the long-awaited series video. I know you're all excited, but so you know, I just watched one of Leon's videos. I'm feeling a little inadequate, um, but I really think this video is going to be good. I think we're going to get a lot done in this video, and now here I am rambling, and now I just think that maybe I should just start. So let's start. A couple ideas that we're going to be talking about in this video. We got the series convergence, we got power series convergence intervals, which was a mouthful. And then we've got Maclaurin and Taylor series. Oh, good, it connected again. Hooray. Maclaurin-Taylor series, which is basically the manipulation of our known series, error bounds, coefficient and nth derivative questions, and a little bit conceptual ideas I didn't list there, but just a little bit of concept stuff. First thing, series convergence. On multiple choice, you're basically just going to eyeball it. You're going to look at it just like you do limits. You're going to ignore all of the terms except the highest degree and see, does that look like a series that would converge once you've done the simplification? Just don't tell anyone that knows more math than me that you're doing that, because they might get upset that you're not doing it rigorously. On FRQs, which I kind of doubt are going to come up, except for when you check the endpoints of an interval of convergence, it's really not going to come up too much. You're really just going to use like alternating series test, direct comparison, limit comparison, or ratio. And the ratio test you're really only going to use to get intervals of convergence in the first place. Provided I remember to do this, I will post all of our tests listed. Remember, I made that PDF a while ago. I'll repost it, provided I remember to do that. So, fingers crossed. All right, let's jump in. Which of the following series is absolutely convergent? Remember, absolutely convergent means I can... Hi, Thor. Absolutely convergent means that I can rip off the alternator and it will still converge. So let's look at A. If that alternator was not there, that would basically be 1/2 the harmonic series. That would not converge. That would be called conditionally convergent. Okay, let's look at B. If I rip off the alternator, that series is a P series where P equals 1/2. That does not converge. Rip off the alternator. Now this one's a little more complicated, but remember, just look at the highest term on top, highest term on bottom. So basically you've got n over n, which is 1. Well, if you add up an infinite number of 1s, that's not going to converge. Which leaves us with only one option, but let's look at it anyway. Rip off the alternator. That's a geometric series where r is less than 1. That is going to converge still. So that is in fact our answer. Which of the following series cannot be shown to converge using the limit comparison test with the series 1 over n squared? So the limit comparison test says that if I take the limit as n goes to infinity for a series over a series, or a sequence over a sequence, if I get some positive finite value, then in fact these series will do the same thing. They'll either both converge or they'll both diverge. So A, again, I'm going to kind of look at it the same way as often as I can. I'm going to just look at the highest stuff on top and bottom. That looks pretty similar to 1 over n squared. So I think that it'd be okay to use the limit comparison test on this. Now this, if I ignore this 5, I've got 15 over square root of n to the 4th is n squared. I have a feeling I could use the limit comparison test for that. C and D are the weird ones. So what I'm going to do for C and D is I'm just going to actually go ahead and write out what the limit would equal, or look like. Now you may not remember this, but I promise way back when we actually did special trig limits. As long as the argument of the sine function is the same as what you're dividing it by, this limit is 1. That's a positive finite value. Limit comparison, or the limit comparison test does not work for that one either, which only leaves us with one answer. But if you did look at that limit, you would have ln of n over n squared over 1 over n squared. Well, when you do the simplification, this ends up just being the limit as n goes to infinity for ln of n, which is equal to infinity, which is not a positive finite value. So the limit comparison test does not work for that one. Hooray! Consider the series -1 to the n a sub n, where a sub n is greater than 0 for all n. Seems like it's pretty important. Which of the following conditions guarantees that the series converges? A. The limit as n goes to infinity for a sub n equals 0. Remember, that is insufficient. 1 over n as a sequence converges to 0, but as a series it does not converge. That's not enough. B. The limit as n goes to infinity for a sub n plus 1 over a sub n is less than 1. That looks a lot like the ratio test, but it seems to be missing the absolute value bars. Aha! Apparently it doesn't matter. B looks good. Let's just look at the other ones to be certain. C. A sub n plus 1 is less than a sub n for all n. So that says that the terms must be decreasing. Well, what if they only decrease to 1? That's not going to work. They have to be decreasing and the limit has to be 0. So A and C combined would make it true, but A and C alone are insufficient. D, the integral from 0 to infinity f of x dx converges where f of n equals a sub n for all n. Okay, a condition for this is that the terms are decreasing. So you need, to use the integral test, the terms must be positive and decreasing. I don't know if they're decreasing. Okay, like we thought, B is the answer. And now we're on to power series convergence. First thing, ratio test and then check the endpoints. Next thought, ratio test and check the endpoints. Ratio test and check the endpoints. So check the endpoints. I don't really think that you guys have much problem with this, so I don't know why I made that stupid joke of, hey, check the endpoints, because you guys check the endpoints anyway. An idea that I don't think I did harp on quite enough is if you have convergence at an endpoint, that's conditional convergence. At least I'm pretty sure it's always conditional convergence. I can't come up with a situation where it's not. That's important because if they tell you like, oh, it's conditionally convergent at 5, well, now you know the radius. The center to that point is your radius of convergence. Anything outside of that range then is going to be considered divergent. Anything within that range would be convergent. So that is a useful idea, and I know we've seen that pop up on a couple multiple choice questions. What is the interval of convergence for the power series? Blah. Oh my goodness, that one looks like a nightmare. But let's just do the ratio test. So we want to do the limit as n goes to infinity. Whoa, n goes to a. What am I talking about? Foolish. I want a sub n plus 1 over a sub n. So let's zoom out so I can see this. In absolute value, I have negative 1 to the n plus 1, n plus 1 plus 2, so n plus 3, x minus 4 to the n plus 1, over n plus 1, 3 to the n plus 1. Now I know what you're all thinking. How is he possibly going to fit the rest of that in that tiny little white rectangle? I don't know. I'm going to zoom in and hope I can do it. So we're going to have n times 3 to the n over negative 1 to the n times n plus 2 x minus 4 to the n. I'll put those absolute value bars there. Whew, look at that. I managed to do it. All right, so now we just got to simplify. Now, I've said this a million times. I'm inside absolute value bars. I do not care about this negative 1 stuff. It's going to go away eventually anyway. So now I've got x minus 4 to the n plus 1 on top and an x minus 4 to the n on the bottom. Okay, so on top I've got n plus 3, x minus 4. On the bottom, I've got n plus 1, n plus 2. And then 3. Okay, so the degree on top is squared if I distribute that, and then the coefficient of it would be absolute value x minus 4. And on the bottom, the coefficient would be 3. So the ratio test says as long as that limit is less than 1, then we'll have convergence. So I need this to be less than 1. So then absolute value x minus 4 must be less than 3. So then negative 3 x minus 4 less than 3. I'm going to add 4 everywhere. 1 is less than x is less than 7. Now all I have to do is check in the original series. If I plug in a 7, will it still converge? Check. If I plug in a 1, will it still converge? Well, see, let me change colors. That way I can try and squeeze it in somewhere. If I plug in 7, this ends up being -1 to the sum of -1 to the n plus 2. 7 minus 4 is 3 to the n over n times 3 to the n. Okay, these 3 to the n's cancel. I've got -1 to the n times n plus 2 over n. I don't think that's going to converge. The reason it's not going to converge is because I essentially just got n over n. That's not going to work for me. Essentially, I'm adding up a bunch of 1s. Now, if I plug in one, I get -3 to the n over n times 3 to the n. Okay, this ends up being the sum of -1 to the n plus 2, -1 to the n, 3 to the n, over n, 3 to the n. 3 to the n's cancel out. -1 to the times -1 to the n times -1 to the n is just 1. So I'm left with n plus 2 over n. I don't think that's going to converge either. I'm looking at C. Neither endpoint converged, which is weird. That usually doesn't happen. I'm flabbergasted, but ready to move on. This is essentially the same idea. If anybody wants to see this problem actually done, let me know. This video is running a little long already, though, so I don't want to eat up too much of your time. So if you want to see this problem, just let me know, and I'll make sure that I do it. All right, let's look at Maclaurin and Taylor series. First idea, we're going to manipulate some known series. Remember, there are 4 that I've told you to memorize. E to the x, sine of x, cosine of x, and 1 over 1 minus x. What you're going to do with those is you're going to take it and then either do a function composition, a multiplication or division, a derivative integral, or sometimes, not very often, you're going to do addition and subtraction. You just do something to the one you already know in order to get the one that they're looking for. Thor, you need to be quiet. Or just make more noise, whatever. Then the error bounds. The only way that we can get an exact value of some function using these series is if we used all infinity terms, which is just not a thing we can do. We always have to stop short, so that's where this error gets introduced. We can't get the exact value, but we can get pretty close. So to get the actual error, we've got our Lagrange error bound and our alternating series error bound. The alternating series error bound is better when the series is actually alternating. If it's not alternating, you can't use it. In the Lagrange error bound, that whole mess that you can see, it's the maximum of the n plus first derivative over n plus 1 factorial a minus 1 to the n plus 1, all in absolute value. N is the degree of the polynomial, a is where you're estimating, and c is the center of your Taylor polynomial. Big thing, I said this before in class, I believe, n is the degree of the Taylor polynomial. With the alternating series error bound, n is the number of terms that you've used so far. So sometimes they'll ask you to use the alternating series error bound, and they'll say, if we used like a 4th degree Taylor polynomial, then you have to figure out how many terms did it take you in order to get the 4th degree. So that's the only place where this gets a little hairy. Other thing, Taylor polynomial coefficients. The general term of a Taylor polynomial is that thing. The big deal being that the nth degree term has coefficient, the nth derivative of c at c over n factorial. So if I want to find, say, the 4th derivative, I need to be looking for the 4th degree term. This comes up as a concept question quite often. Also, they may use the general term of a Taylor polynomial to get you to construct it by giving you f and f prime and f double prime, things like that, values. That felt a little rambly. I'm sorry if it was. Let me just do some problems and maybe that'll make it up for you. Third degree Taylor polynomial for the function f about x equals 0 is this thing. Which of the following tables gives the value of f and its first three derivatives at x equals 0? Okay, so for this I'm going to channel my inner Spencer Bishop and I'm going to recognize, oh, look at that. These third derivatives are all different. So if I find the third derivative, I found the answer. So let's do that. Let's find the third derivative. The third derivative should be paired with the third degree term. So it should have coefficient f triple prime evaluated at 0 over 3 factorial. That's what the coefficient of the third degree term should be, based on the definition of a Taylor polynomial. If I look right here, though, I can see what it actually is. It actually is -3. Well, now I can use this in order to solve for what f triple prime is. 3 factorial is 6. So if I multiply that over, I get f triple prime at 0 is -18. Okay, that eliminates that, and that. The answer is C. Thanks, Spencer. Enjoy your cereal, because that's all I imagine you doing. Eating cereal, nothing else. I'm sorry. The function f is defined by the power series this thing. Find the value of f double prime 2. Same idea. Second derivative evaluated at the center of the Taylor polynomial. It should have, the Taylor polynomial for the second degree term should have this coefficient. The coefficient actually, if I look at this term, is 1 over 3 squared times 3. So then f double prime of 2 divided by 2 should be 1 over 27. Multiply the 2 over, and I get that the second derivative at 2 is 2 over 27. Ta-da! Use the first three non-zero terms of the power series for f to approximate f of 1. Use the alternating series error bound to show that this approximation differs from f of 1 by less than 1 over 100. Okay, so this is that thing I was telling you. I'm going to stop short. I can't make it to infinity, and then I can show you how far off I am by at most. I could be spot on. Chances are I'm not. Use the first three non-zero terms, so we're going to take the first three non-zero terms and plug in 1. So I got 1 plus 1 minus 2 over 3 times 2 plus 1 minus 2 squared over 3 squared times 3. So that's 1 minus 2 is -1 over 6. And then I've got 1 over 27. Find a common denominator. 54 minus 9 is 45. Plus 2 is 47 over 27. Yes. Okay, now it says use the alternating series error bound to show that this approximation differs from f of 1 by less than 1 over 100. Alternating series error bound. I'm just going to use the next term and plug 1 in. So it's going to be 1 minus 2 cubed over 3 cubed times 4, all in absolute value, which is going to be 1 over 3 cubed is 27 times 4 is 108, which is in fact less than 1 over 100. Hooray! Write the first four non-zero terms of the Taylor series for sine of x about x equals 0, and write the first four non-zero terms of the Taylor series for sine of x squared about x equals 0. Okay, I should have sine of x memorized, or at least the general term, so I can generate some terms from it. The general term for sine of x is -1 to the n, x to the 2n plus 1, over 2n plus 1 factorial. That looks like a nightmare. Who let me write with a pen? That's closer. Okay, so I'm just going to generate the first four non-zero terms by plugging in 0, 1, 2, 3. That's going to end up being x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial. Those are the first 4 non-zero terms of the Taylor series for sine of x. Now I'm going to use those to write the first 4 non-zero terms of the Taylor series for sine of x squared. That means every time I see an x, I'm going to put x squared instead. It's just a function composition idea. So sine of x squared is equal to x squared minus x squared cubed is x to the 6th. X squared to the 5th is x to the 10th. X squared to the 7th is x to the 14th. Oh, that should have been minus. That's it. That's all there is to it. Just a little function composition. If they had said find x sine of x squared, the next thing I'd have done is just multiply everything by x. If they said find the derivative, I would have found the derivative of it just using power rule. Believe this is the last thing? It is. Okay, cool. Let's look at it. The function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. That seems redundant. Isn't that the definition of the interval of convergence? I'm sorry for the aside. It's late and I want to go to sleep. It is known that f of 1 equals 1, f prime of 1 equals negative 1/2, and the nth derivative of f at x equals 1 is given by the nth derivative of 1 equals negative 1 to the n minus 1 factorial over 2 to the n. Write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 1. Done. Let's get it over. Let's do it. Okay. Remember, every Taylor series looks like this. For us, it's going to be at 1 over n factorial. For us, x minus 1 to the n, because we are doing it about the x value 1. Okay? The 0th derivative is just the function value. So I'm going to have 1 over 1 factorial x minus 1 to the 0. That's the n equals 0 term. Plus the first derivative, so negative 1/2 over 1 factorial x minus 1 to the first. Plus the third derivative. I'm going to have to go to this formula right here that they gave me. I've got to plug in 3 to it. So when n equals 3, I'm going to have negative 1 cubed, so that's negative 1. And then 3 minus 1 factorial, that's 2 factorial, so 2. Divided by 2 cubed is 8. So that's negative 1/4. So I got negative 1/4 over 2 factorial x minus 1 squared. Why did I plug in n equals 3 term? Who let me do that? Anyway. Is my webcam not working? Oh, it's back. Okay. So we'll save that for a second. For n equals 2, I'm going to get negative 1 squared, so it's just 1. 2 minus 1 factorial is 1. Over 2 squared is 4. So 1/4 over 2 factorial x minus 1 squared. And then we've already got that n equals 3 term from when I made a mistake, because I do that once in a while. And it ends up being minus 1 over 4 over 3 factorial times x minus 1 cubed. Okay, for the general term, because it wants that as well, I'm just going to use the nth derivative thing that they gave me. The general term is going to be negative 1 to the n minus 1 factorial over 2 to the n times n factorial x minus 1 to the n. Now there may be some pattern that I'm just completely missing, but I'd rather just save my time. Nth derivative over n factorial, that's this part here, times x minus 1 to the n. That's it. Okay, sorry this went on a little while. Sorry I got tired and rambly, but hopefully I can live up to Leon just even a little bit.